Yeah, so I'm Maxim Kontsevich, and I will speak about ZPL action from birational geometry. So my talk will be it has the same title as another talk which I gave kind of a couple of weeks ago on another seminar, but it will be slightly different, and if you heard one of them, it will be not identical. Yeah, so what I'll talking about? Let me start with some definition. Suppose I have some field K and extension, which will be finitely generated extension. So it will be finitely generated extension. It means that field K is isomorphic to field of rational function on some algebraic varieties, but there are many varieties. X could be smooth projective variety of certain, let's say, transcendence degree of K, big K or small k denoted by n, and will be dimension of this variety. But there are many such varieties. Each such variety, which we will call something like a model. Maybe I choose a different color. I think it's in a second. Of K. Actually, it's a model of K. Oops, sorry. So there are infinitely many models, and for each model, one can associate a set of divisors of kind of a set of irreducible divisors in X, kind of the risky points of codimension 1, and then we denote by a set of divisors of K, which kind of independent of the model, which is inductive limit over all models. And how inductive limit is formed? If we have, for example, some dominant birational map from one model to another model, then a set of divisors of X prime is set of divisors of X, and union of some finite set, which is called exceptional divisors. You add new divisors, like blow up a point to get, or some variety, you get new divisors. Exceptional divisors. Yeah, so we get some abstract infinite set associated to this birational type. And now I go to another thing. Suppose I have omega, which is n form of my field over K, which is non-zero. So for any given model, omega gives a rational top degree form, a rational volume form. On X. And then, of course, this form will have zero poles and zeros along some divisors. You get certain function, ord omega, from divisors of X to integers, which is finite support. On a given model. But then if it's compatible with blow-ups, so one can have a function from all divisors or divisorial relation of big field to integers. Okay, so I get this function, and the first definition that omega is a logarithmic form if values of this ord belong to the set -1, 0, 1, and so on. So it can have only poles of first order, no more than high order. It doesn't depend actually on choice of, we can speak about function on smaller space, diff x, or larger space, diff k, and the function is the same for all. This property does depend on the model. So this, if it's logarithmic in one model, you make blow up, it will be still logarithmic. And the main definition, which one can add here, for logarithmic form, one can consider set of these divisors on all possible models where the value is -1. You get certain set. I will not denote it at all. Oh, by the way, Daniel, are participants muted or not? I think they're all muted, yeah?
Yes, they're all muted.
Yeah, actually, I think it will be safer to unmute people than if you...
No, but you can unmute yourself, so it's not prohibited.
Yeah, no. The problem is I should unmute from... okay, maybe I don't know how to... It's a bit complicated for me to unmute. Oh, Daniel, can you just unmute everybody? Yeah, just it will be easier to have. Or people when people want to start, they just unmute themselves. Okay. Yeah, so we have the set. How it denoted, maybe something like skeleton. The set. I'll denote skeleton of k omega and maybe called primitive part. How it looks like. So the basic example which we should look at, it will be the case field of rational functions in n variable. Yeah, for example, if is your variety, you can choose x is, say, toric variety containing torus with coordinate x1, xn, and form omega will be this logarithmic volume form on a torus. X could be any toric variety, and if you have a toric variety, then all toric divisors will on all toric divisors this form will have pole of order 1, but then one should go to all possible limits. And for example, even one can consider n equal 2. Let's for example, x will be p2, and you get 3 divisors when you have poles of order 1. But then one can start to make blow-ups. I don't know which color to use. Choose it, make blow-up, and then another blow-up. You add more and more toric divisors, and all of them, this form will have pole of order 1, and eventually the set of skeleton, the skeleton primitive part, will be n-dimensional integer vectors which are primitive, which don't have any non-trivial positive strict bigger than 1 common divisors, the coefficients of this vector. So it's the n minus 0 and minus all divisible vectors. Yeah, so that's a basic example, and you see that one can make divine set of skeleton. Non-primitive will be at, say, kind of like 0 and plus non-negative integers multiplied formally by this set. And in this case, we get whole z to power n. Yeah, so that's kind of more convenient picture. You get z to power n. by definition, because the construction is natural, Birational maps, automorphisms of K preserving my volume form, this group, they act on the skeleton, primitive or non-primitive part. And the claim how it acts, for example, in our example is claim for, again, K equal to the historic example. The section is, sorry, oops, something wrong. The section is by piecewise linear with integer coefficients homeomorphisms of Rn containing Zn, which are homogeneous of degree 1. Yeah, so that's there's just an example of such a map. When n equal 2, you can have a map from Rn to R2 to R2, which goes, let's say, from coordinates, it's called, I know, A1, A2, goes to A2, absolute value F2 minus A1. That's interesting map of period 9. And it comes from many birational maps preserving volume elements. For example, x1, x2 goes to x2, and x2 plus 1 over x2 divided by x1. Yeah, so it's this x2 plus 1 over x2 represent absolute value of f2. So the general rule is the following. If we have a map, x1, xn goes to p1 of x divided by q1 of x, q2 of x divided by q2 of x. So rational map is given by a bunch of rational functions for finite variables. Each rational function is a ratio of two polynomials. And then what you do, you if you have this points a1, an to r, now in Rn, where it maps, what is the corresponding map? You imagine that xi's are something like t to power ai, and t goes to, let's say, infinity, or like a real number going to infinity if you are over complex numbers, if case c. And when consider generic values of ai's, you substitute to this polynomial, so it will grow, some monomial will be dominant, you get this point. Okay, so we have map from AI to BI, which is ZPL map. Yeah. Now I will just make few remarks. For n equal 2, when consider ZPL homogeneity degree 1 maps from R2 to itself. So how it looks like, you divide your plane by finitely many angle sectors with rational direction, and then map to some kind of slightly different collection of sectors. And on each sector, the map should be maps from SL to Z. Yeah, so we have this group, and actually it's a really funny group. It's equivalent to something called Thompson group, which has a different descriptions, which is maps from R mod Z to R mod Z, which maps points with kind of which are have denominators which are powers of 2 to itself, and all derivatives, which are the homeomorphisms, which will be piecewise linear, but in dimension 1, and all derivatives belongs to 2 to power Z. It has some description related to number 2, this Thompson group, but it has a different realization as X maps by piecewise linear transformation of R2 to itself, or from a sphere double cover of RP1 to itself. Yeah, so it's famous group in group theory. And what we see is that we have high dimensional generalization of this story. Yeah, actually I want to, before going to this more general thing, I want to say something related to cluster varieties. Namely, in the case when k is equal to my main example, and with volume element, we can consider not only preimage of -1, but also of 0. We get certain huge set. Let's denote this set S. It's huge set. It has infinitely many parameters, and the group also acts here. Birational transformation preserving volume element. So this set has actually pretty funny picture. So choose isomorphism, choose a model, choose that kind of torus, kind of k star to power n roughly, or better, gm to power n. Kind of toroidal model of I think it should be smooth but not proper model. So like this coordinates. Then this S will contain ST, which will be divisors in a torus. Obviously, because on each divisor the form has no zeros or no poles. On divisor on non-compact torus, it's kind of non-compact, smooth, non-compact variety. But how the rest of the set look like? The claim is that S minus ST is disjoint union over all primitive vectors, which are exactly skeleton k omega primitive, which will be the n primitive. Sorry, it's my capital N, of non-negative integers. It's similar to what we have, how to construct non-primitive things with non-primitive. Formula multiplied by set of divisors of, let's say, n-1 dimensional torus. Certain canonical n-1 dimensional torus. how it looks like. Namely, maybe I explain first in case of the second, in the case of n equal 2. Now suppose we have coordinates x1, x2 on my torus. Then one can have this primitive vector 1, 0 in Z2 correspond to divisors which obtained by the following way. For example, we can make a model like P1 in x1 multiplied by P1 in x2, make projective model, and consider divisor x1 equal to infinity and x2 arbitrary in P1. We consider such a divisor at infinity. It's a divisor in my form has pole, but now consider any point here. Let's say take point in my field, and then make blow up at this point. And we get some exceptional divisor on which form will have no zeros, no poles. And similar situation can happen in high dimensions. Namely, you have now n coordinates, x1, xn. Let's say this my primitive vector is 1, 0, 0, 0. And now I have divisor x1 equal to infinity. Let's take the product of projective place. But now x2, xn we lie in GM multiplicative group to power n minus 1. And here we put arbitrary divisor in this torus, write some equation, p of x2 xn is equal to 0, where p is irreducible polynomial. It gives me a certain divisor sitting here. And then when we make blow up, we get exceptional divisor. But now one can make blow up not once, but several times. It's already interesting in dimension 1. One can make some point like infinity constant, make blow up, make another divisor. Yeah, and order of my form will be -1 and 0 because an exceptional divisor will have no zeros, no pole. Now make blow up a new point. Get here again, make blow up a new point, and the number of times how many times you make blow up, it will be this integer parameter which I mentioned before. Okay, yeah, so I get this nice description, and then there's really very cool geometry here goes on. Claim that for any divisor D, which belongs to evaluation -1 of number 0. So divisor where my form has no zeros of pole. We have a canonical automorphism of my field K, which makes the following. So let's return to the things. We have huge set S, and how we have this set ST related to the torus. Such that canonical automorphism phi d with the property is the following: that phi d of D belongs to S, and what really happens, and phi D of S differ from S only at one point. Phi D of S will be, let's say, a second. Will be S minus some point. The second phi D of S plus some another point. And what really goes on, I have to say that I have this, phi D of ST, change a set of ST only by one point. So what the picture is the following: you get this huge space set S, inside you have space ST, you get some point of S which is outside of ST, and then it belongs to some orbit of my group, which this orbit of there will be certain element of my group which has some point on ST maps goes outside, the rest goes to itself, and by certain permutation, and there will be some semi-infinite orbit which, after some iteration, move my divisor D inside the point ST, and then it goes outside of ST. And I'll just write the formula for this transformation. If my primitive vector D was described by primitive vector correspond to primitive vector 1 and 0, some irreducible polynomial n minus 1 variable, and some multiplicity coefficients k greater than 1. Then with the transformation you consider will be the following: it will be x1 goes to x1 multiplied by px2 xn minus 1 to power k, and x2 goes to x2, xn goes to xn. So you get this transformation, which is power of k's power of transformation, which you can put k equal to 1, and this for example, the divisors which sitting in a torus, which will be divisor in k to power n, is given by equation px2 to pxn equal to 0. So it's some kind of tube. It doesn't depend on coordinate x1. And yeah, so it will be some kind of canonical way to put these divisors. And you see, it's really very remarkable geometry. You get big set S, you get collection of certain things like ST, and you have something similar to axiom of matroid. This ST one can call basis of matroid, like basis in the vector space. And there's something called exchange axiom. If we have a basis in the vector space, some collection of vectors has a basis, and we get another vector which is not on the basis, so you can remove some vector from the basis and replace by vector in your the old vector by in U1, and you see that here get something like d0, d2 will be equal to dk, so it will be maybe labeled by integers. So the picture is that conclusion is that st minus d0 union dk is st prime, bt prime is another toroidal model. Yeah, so the whole story one can rephrase in the following way. A second. So we have a conclusion from all this picture is the following. Consider a subset in S, subset kind of like called it maybe call it something like big X, which is ST union certain finite set. The number of elements is not related to dimensions, it should be anything. The ST is isomorphic to divisor of a toroidal model. Now, for each element AI, one can apply this canonical when one has this ST union of DAI is equal to S of certain new model union of certain X to 1 divisor. So it means that you represent the same set as a union for each I. You can represent the same set as union of toroidal model plus again finite set, which can have the same number of elements. And what is going on? It's kind of big generalization of cluster mutations, I have to say. It's called Lampilavsky, something like this, mutations. Namely, what you do, you consider set X big set as above and define cluster in the set is a finite subset which will have whose complement is isomorphic to divisors of toroidal model. And then for this cluster, for each element, one can make a new cluster, remove this element, replace it by something else, and get a new cluster, and you get a regular n-valent tree. You get huge regular tree, which maps to a set of clusters. And then it can happen that if you make many mutations, you get object isomorphic to original one. And isomorphic, it means you get some birational maps. And then you get huge groups acting by birational automorphisms. So the usual cluster geometry corresponds to the case, kind of very special case when you have some skew-symmetric form on a lattice, and so the torus will have Poisson or structure or two form, and what you do, you these divisors in the n- dimensional tora are given by some canonical like hyperbola like equations, some monomial plus 1 equal to 0.
Why you get it in the finite time?
No, you get not finite type. These things, you see that you get mutation. It is defined on some kind of so the cluster data will be given by some different data. You get just collection of primitive vectors, some integers, multiplicities, and some decomposable reusable hypersurfaces and minus one-dimensional tori. And here one can make mutations as long as you wish, and also one can make certain function. For example, if you get this finite set X, you can see the algebra of functions, of rational functions, which have no poles at divisors belonging to X. So it will be Laurent polynomials. In particular, this algebra function will be automatically subalgebra functions in Laurent polynomials. If you make toroidal model, because I said it's a function not vanishing any divisors in toroidal model, it means that it's a polynomial. It has no poles inside the torus, so it will be Laurent polynomial. But this extra divisors put extra constraints. This algebra could be. It's not clear what it could be, but it's if it's sufficiently big, then you get this cluster variety, and you get Laurent phenomenon for free, because the same algebra will be embedded in Laurent polynomials in infinitely many ways. Yeah. So it's kind of a side remark, but you see that it's in this geometry we have this piecewise linear action. Studying divisors when a form has pole of order 1, but pole of order 0 or kind of regular points are also interesting game, and maybe one can look of that, should look on them in more general situation. Yeah, so that was all story about toroidal case. And then I'll talk a little bit about some other examples, namely some kind of relative or non-Archimedean story. Suppose now my field is non-Archimedean. And I'll just assume for simplicity that it will be something like Laurent series in one variable, and complex coefficient. The definition is very general, but let's assume simplify my life in this way. Then if I have n-dimensional variety over K, then I can make a model in a slightly different way. Suppose we have variety over K, then we have model of variety, not of field. It's something over a ring of integers, which is oh, sorry, it's actually, I used the wrong letter X before. It's called X0, or ring of integers. And if we are in characteristic 0, one can assume that we have divisor with normal crossing. And then one can make certain model of my variety, which maps to this spectrum of C of t. And if we have form omega, we should multiply by dt over t, and maybe by t to some power. if omega has logarithmic poles, there will be unique power such that this thing will also has logarithmic poles, and we take and also has logarithmic pole at least one of device and special fiber. So when we make this model, then one can have these divisors with first of the pole, both vertical and horizontal one. And now the game is consider look only at vertical divisors in all possible models. At which form has form multiplied by dt over t has pole of order 1. And then we get certain set, and the claim that the set will be essentially like it will be it is set of rational points in compact PL or integer PL space. I will describe you in a minute. Namely, choose any model such that special fiber has a simple normal crossing, or whole model has simple normal crossing. So we got both vertical and horizontal divisors, and now consider set of it's some divisors. My form will have poles of order 1. It's some of pole of order 0 or 0 of order 1, and so on. And what one should do, what should start to make blow up only along intersection of divisors when my form has pole of order 1. So we make blow ups only at such thing, and what we gain by this, we get something like Fourier fractions, and we get points parameterized by integers or rational numbers, and the claim is you get part of the following set. Maybe I'll just describe you on a situation kind of opposite to what I considered. Omega has no poles at all on X. Okay, has no poles at all. But when I make a model multiplied by dt over t, this thing start to have some first order poles. In this case, the situation is the following. So we had X0 and contains special fiber, which will be union of certain finitely many divisors, some finite set. And now what we do, we should do the following. We have among this consider I such this is the I order of poles of Z1. Homogeneous, we consider collections of Y1 AK such that order of the I1 okay is equal to is 1. We have poles of order 1, and intersection is non-empty. And by assumption, because simple norm closeness should be irreducible variety. So get this special collection of indices, and now what to consider is this: consider simplex spanned by set of I, and contain closed simplicial subset spanned by simplices by all this intersection of divisors when you have this property. And you get certain finite polyhedral complex, and the claim that this all divisors in all models and have poles of order 1 will be rational points on this variety. So, so it will get essential skeleton. And rational points will be all divisors in all models where one has first order pole. Sorry. Oh, sorry, I forgot. In this situation, one should also allow to your field to go to add some extension of your field. Yeah, so get this piecewise linear space, and again automorphisms of X preserving omega X by piecewise linear map is based on essential skeleton. Yeah, so one can study this example yeah, for example, if when X is case-free surface, then essential skeleton is diffeomorphic to S2 or homeomorphic to S2. For this essential skeleton, one actually get certain map to non-negative integers, namely this number D, which I draw before, degree D of extension to which of the local field, which you need to get this point. So how it looks in real life, I describe you this in terms of this nice model, and when you get this polyhedral object, then consider points whose denominator this things will be denominator of this rational minimal possible denominator of the point of rational point. Kind of, let's call it denom, this map. Denom is least common multiple of denominators of coordinates. Particularly, if consider points with denominator 1 will be just vertices of the simplest, then consider kind of half integer points and then that's a set. So for each denominator, you get finite set. And the conclusion is that automorphism of X omega maps to automorphisms of finite sets. If my variety is compact, if my form has no pole, if it has poles on a variety, then the set will be infinite. But now shift gear, go to finite sets. for each integer greater than 1. And for example, if we start with case-free surface, one can, over this C of t, one can use Torelli's theorem to describe what are symmetries of case-free surface in terms of lattices. And then one get a certain huge group. And the group is, I will not go to the details. So the group is arithmetic subgroup in SO118 R. Actually depends on some parameter, but and then in the simplest case, this order of elements of this finite set, if we have a denominator is equal to D, then this arithmetic group maps to symmetric group acting on a set of D squared plus 2 elements. Now, so it's really kind of pretty amazing. You get arithmetic subgroup in kind of SO118 with integer coefficients, maps to symmetric groups of such orders for any D greater than 1. And as far as I understand, it's not going to through congruent subgroup. It's really through this construction, which I explained. Yeah. Oh, by the way, this case-free surface example was described in big details in a very old paper of Jan and mine. It was archived a long time ago. Yeah, so
should write Z and not R.
So arithmetic group, yeah, it's kind of Z, but I should say, yeah, it's arithmetic subgroup in a real group, but it's some kind of version of SO118Z here. Say.
Thank you.
Yeah, yeah. So there's this construction which is pretty interesting, and it wasn't studied yet, so people didn't look at. One can make even computer experiments with this, but. We have two descriptions here. Yeah, and there was also a big generalization of this kind of explicit examples when some have group acting preserving some volume element. This is a very funny construction which I had also for many years, which is the following one. Consider any D greater than 2. And consider a regular graph of degree D. For example, D equals 3, you get a 3-valent graph. Whatever. And for each edge, we associate some certain parameter. So my variety will depend on this parameter. But we'll first think about real numbers. LE belongs to some parameter, belongs to my field. If k is equal to r, which is not non-archimedean field, but you can think about it as a length. And now consider space of configurations of graph, kind of vertices sitting in RD or sphere to dimension D. Set it up to rotation group or for sphere or Euclidean group and Euclidean space. Set that each edge has a given length. We get a certain set, and it's clear that it's algebraic variety, and one can replace real numbers by any field. We just consider coordinates of points and write equation sum of square of length is equal to given number. The claim it is Calabi-Yau. Calabi-Yau variety, it has canonical volume form. And the volume form is kind of obvious. You have have some coordinates, you get system of equations, and I get a group. And group is, has left and right invariant volume element. So you just consider product of d of coordinates divide by differentials of equations and divide by volume element of the group. So you get a Calabi-Yau, and it has a huge symmetry group, Birational symmetry group. Namely, if you have, let's do picture in D equals 3. Imagine that in 3-dimensional space you get three-valent graph, and you get some vertex V. Then for each vertex, one can draw a plane which contains this vertex, and now make kind of reflection. You get you make reflection with respect to this plane. You get the same distances, and you don't change any all other points. So if you have your three-valent graph, you make a new three-valent graph replacing by 3 edges by another 3 edges. And you get a lot of this. It's easy to check that this symmetry preserves volume element, and you get group generated by reflections for each vertex. And if vertices are not connected, then this element commute. If they're connected, then do not commute. And it will be Coxeter group. When you put infinity on each edge, it means that the product of two involution will have order infinity. It's just no relation. But if they're not connected, then to the order, they will commute. So you get huge Coxeter group acting on your variety. And now imagine that Li case non-archimedean field, I element in this field of certain norms. Then one can theoretically produce equations and so on, and get this essential skeleton and get the section of huge groups on by piecewise linear transformation of certain spheres, complex spheres. Yeah, again, it's completely uncharted territory, and everybody is welcome to explore it. Okay, thank you. Okay, so I think, am I connected? Hello?
Yeah.
Okay, yes. Yeah, so if you have some questions, I'm happy to answer.
That's self-service. Yeah. I have a short question about this Matroid story and generalization of class. So for usual cluster varieties, yeah, you can somehow quantize.
Yes. Yes. When quantize, it means that on your torus you get Poisson structure, and here it's kind of very weak. You have only volume element. It's
so there is no non-commutative.
Yeah. If you want to have quantizations and you want Poisson structure, I think you're more or less obliged to. It's still more general than usual cluster varieties, because we can have more complicated hypersurfaces in n-1 dimensional tori.
So no chance to see generalization of quantum logarithm.
No. It's one should have kind of really. Let's try to think what's going on. One have to study the condition on the hypersurface to be the properties when make blow up. This Poisson structure has no poles. It's not obvious. It's some property of hypersurfaces. Yeah, I suspect it, at least when this Poisson structure is not degenerate, you should get only usual cluster varieties, maybe with parameters, frozen variables. Yeah.
Okay.
Hey, I also have a question about a generalization of this cluster variety story.
Yeah.
Is it possible to blow up inside the divisor? You're blowing up a hypersurface. Is it possible to blow up something in higher codimension too?
No. In this description, if one can make blow up as as you like, but if you make blow up in a subvariety of high codimension, then the volume form will have 0 on the exceptional divisor.
But you are allowing blowups along hypersurfaces more general than ones usually allowed in the
Yes,
cluster
any
varieties.
hypersurface in any hypersurface in a toric kind of hypersurface, something of codimension 2, will be okay with the volume element.
Okay, thanks.
Yeah, also I have another short question. In that story of the essential skeleton, there is a question when there is a projection from your variety to the skeleton, yeah, kind of non-archimedean integrable system. Yeah, for this last example with the graphs.
Yeah.
What are the conditions which guarantee? I mean, it's not always, yeah. You need to choose something.
That when consider the birational symmetries, they do not preserve the structure of integrable systems. They destroy it. Yeah, so it's.
Yeah, but I mean just a projection.
Projection? No. I don't think it's a subset of Berkovich spectrum, but not a quotient set naturally.
So then there is no, in general, there is no projection, like no analog of Keller's. Okay.
Yeah.
Okay.
Yeah. Also, just it's a kind of side remark. When you have this regular graph, you can try to think it's quotient of some infinite regular tree, but I don't see any relation between this regular graph and regular tree, which was in cluster geometry picture. It's kind of accidental.
Okay, thank you.
Yeah. Okay, thanks.
Thank you.
Thank you.
Thanks for the talk.
Thank you.